My name is Fawad and I will be conducting this session on the introduction to SAP 2000. It is a commercial software package generally used all across the world for structural analysis applications, for analysis of buildings, bridges, any kind of structures. And it is a software product from a company named Computers and Structures, shortly known as CSI. It is a US based software developer company. So, the complete name of this package would be CSI SAP 2000. So, I will be conducting a quick demonstration on how you can use this program, how you can conduct analysis of simple or even complex geometries of different structures. It's, as I said, is a general purpose computer program to perform different process of computer simulation of structures. It might include modeling, analysis and design of structures also. So, it have some capabilities related to the automated structural design also. It is a product from CSI, Computers and Structures, and it provides the features to model fairly complex geometries, integrate types of structures. It allows you to apply different types of loadings on your structures. They can be static or dynamic, or it also allows us to perform different types of analysis. They also can be static, dynamic or some other advanced analysis types. So, it is one of the most commonly used commercial package, and this company Computers and Structures also own several of the other most commonly used programs. For example, CSI ETABS. ETABS is a structural analysis program which is mainly used for analysis and design of building structures. Similarly, they also own a program called CSI Bridge for the analysis and design of bridge structures, and CSI Plant for industrial structures. But SAP 2000 is their flagship program. It is the oldest program, the first program which was developed for general purpose analysis, and then later on it was customized for buildings to develop ETABS, customized for bridges to develop CSI Bridge. So, all the other programs from this software company actually use the analysis engine developed for SAP 2000. So, what we can do is that I can give you an overview of the computer program first, its capabilities, what are some of the inputs required to model any structure or any beam, frame or even 3-dimensional structures, and then we can go to the program in the second part of this session, and I demonstrate you one example, one beam or frame example, and then carry out its analysis under some static loading and then show you some of the results, right. So, if we start with the typical routine process for any structural engineer, we know that we start with trial geometry or sizes of the structure, right, of structure, and then we also start with the trial material properties, right. So, trial material properties and all the other inputs which are actually required at the start of this whole process of structural analysis and design. We start with their trial values, and then on the other hand we also have the applied loading, right. So, we have applied loads or a reasonable estimate of the anticipated loads which can be experienced by your structure. So, we have applied loads, right. We carry out a process using these two pieces of information to convert those applied loads into the load actions. This process which we convert from loads to load action is actually our structural analysis process, and this is what you are actually studying in this course, starting from a simpler case to a more complex case in later courses. So, this process of structural analysis is actually converting applied loads with trial geometry, trial sizes, trial material properties into what we call as load actions. Load actions can be many. For example, they can be axial forces in different elements, right. they can be bending moments M in different elements of the structure, they can be shear forces, they can be even strains in a particular element, they can be rotations, torsional moments, and all the analysis results which you can think of, we actually call them load actions, right. So, applied loads can be in the form of concentrated loads or point loads, right. They can be in the form of uniformly distributed load or uniformly varying load, they can be even dynamic loads also, right. So, there are different load types. Process of structural analysis actually convert those loads into what we call as load actions. Load actions can be all the internal forces, they can be any effect of the applied loading on our structure. So, strains, rotations, deflections, for example delta at different points in the structure, they are all the analysis outputs or load actions. Then obviously the process does not end here, the analysis is not end in itself. The purpose of analysis is to conduct what we call as structural design, and the design output we know already is the final geometry or sizes, right, or final material properties to be used plus final material properties, their amount and their properties to be used, right. This process of converting load actions to the final geometry, final sizes, final amount of reinforcement, final cross section shape, this is actually structural design process, right. So, this is our routine thing which we do on daily basis. Structural design is obviously to make sure that whatever you finalize on the right hand side of this equation is able to withstand all the load actions, right. And obviously, as I have said that it looks like a one way process, but actually it is an iterative process. You may end up in revising some trial geometry, for example, right, this thing, or you may also end up in doing some design decision making which modifies the applied loading also. So, in that real project case, you have to perform that process in an iterative manner. So, you can modify something towards the end and then carry out the process again until you reach to the final geometry or final sizes which will be implemented in field, right. So, in that process actually we are here in structural analysis part, and obviously the later part of this big process will be covered by several other courses. If you classify whatever you have discussed up till now, you know that the analysis of determinate structure does not require much effort, you only need equilibrium equations to solve them. So, if you have the structural analysis of determinate structures, obviously for that you just need equilibrium equations, but for indeterminate structures you actually have several methods to perform structural analysis, and they can be classified into either classical methods or approximate methods. In this particular course you might be familiar with, for example, flexibility method or slope deflection method to solve for indeterminate structures, slope deflection method. Then one very common method for indeterminate structures is moment distribution method. So, these are all classical methods which allows you to actually solve for any load action, for example, bending moments, shear forces for indeterminate structures, and the list continues. Actually, there are many other methods in this category, but the commercial programs, the structural analysis programs which are used for real projects do not use any of those classical methods for indeterminate structures. Your real building project or a bridge project will always be an indeterminate structure. It will be having many restraints, and it will be a heavily indeterminate structure, and you need to use a computer analysis program to determine bending moments in different elements, shear forces, deflections, rotations, and so on. So, that commercial program whichever you will use, it will in almost all the cases won't be using any of the classical methods. It will be using a method called finite element method. Finite element method, you will be having a course, an elective course on this particular topic in your 4th year. This is a method which almost all of the commercial structural analysis programs, either in civil engineering or mechanical engineering, they use this method, right. And if I just give you an overview of what is happening in that method, you are considering the full indeterminate structure like a very complex or a very big spring. So, we are all familiar with the Hooke's law, F is equal to Ku. We know that whenever we apply a force F to a spring, it deforms by a quantity u, and the relationship between F and u is actually mainly related by a constant quantity which is stiffness of that spring. We can call it spring constant, and that K value is dependent on what material that spring is made of, what geometry or thickness that spring has, right. So, K quantity is a constant quantity which is the stiffness of spring, and it is relating the force with the resulting deformation. We actually perform the same thing in finite element analysis at a very large scale. We assume or think of our structure as a very complex spring, but it has stiffness in all directions, actually in all 6 degrees of freedom if you talk about all 3 dimensions. So, we have applied loading which can be lateral loading, vertical loading. Using that information, we construct what we call as the F vector. So, it is a vector which is having an order of degree of freedom by 1. So, it has as many entries as the degrees of freedom in that structure. So, all the applied loading can be used to construct this F vector. Similarly, all the deformations, the deflections of all the points in the structure is represented by a u vector, and again it is a degree of freedom by 1 vector. So, this is a vector containing all the deflections at different points in the structure. Both of these vectors are related by a matrix called K matrix or stiffness matrix, and it has an order of degree of freedom by degree of freedom, right. So, this vector is equal to that K matrix, F vector is equal to that K matrix times u, right. So, you can imagine that if you have a 50-story building with thousands of points in that structure, that K matrix would be like 50,000 by 50,000 or maybe even more than that, right, a very big large matrix. Similarly, F vector will be like 50,000 by 1, same is deflections. And then this K matrix is a function of the material properties, cross sectional sizes, structural geometry, configuration and everything, right. So, all the information about trial geometry, trial materials, trial sizes will go into this matrix to construct K matrix. The program actually will be doing it for us. All the applied loading which we will be applying to our model, the program will use that information to construct this F vector, and then we press run analysis. The program will simply be determining u as K inverse times F, right. So, it will simply construct K matrix using the given geometry, given material properties, given sizes, and it will inverse that matrix, multiply it with the F vector to determine all the deflections at different points in the structure, and then further that information, that deflection can be processed back into internal forces, reactions and all other outputs of structural analysis. So, this is what is happening in a commercial computer program when you just click run analysis after drawing your structure, right. So, when you are drawing your structure or modeling your structure, you are actually giving the information to the program to construct what we call as the global K matrix of the structure. When you are applying point loads, uniformly distributed loads or area loads, you are actually giving the information to all the programs to construct what we call as the F vector, and when you click run analysis, you are actually asking the program to solve this equation, which may take maybe many hours also, depending upon the complexity of your model, depending upon the applied loading type and all that, right. Now, the program, when it implements finite element method, all of them, they know how to construct K matrix using the given information from user, and that includes again material properties, cross sectional sizes, and the geometry of the structure, like length of all the members and heights and everything, right. So, just to give you an example, what is that K made of? Stiffness matrix. If you have like 10,000 elements in a real structure, the program will construct the local K matrix or a small stiffness matrix for each of the 10,000 elements, and then assemble them based on how the real structure is constructed to make a global K matrix of the order degree of freedom by degree of freedom. So, just to quickly give you an idea what this stiffness matrix K made of, for one element I write its K matrix, which is a 6 by 6 matrix, because this element have 6 degrees of freedom, 3 on this node or this end and 3 on the right side or right end, right. So, if you look closely, they are constructed, or K matrix is constructed from 3 types of properties. One is elastic modulus, which is a material property, cross sectional area of the element. This must have some cross sectional area if you cut a section, right, and the moment of inertia, which is also a function of the cross sectional shape, right. For rectangular cross section it is like BD cube over 12. So, both of these properties are like cross sectional shape properties, and finally the length of that element, which is actually the member property, how long that element is. So, you just need these 4 numbers to construct this K matrix for this one element. So, imagine that you have a building which is composed of like thousands of such elements, we call this as frame element, right, and each of those elements have this 6 by 6 matrix, and then what program is doing, it is simply constructing using this information the global big K matrix, maybe 10,000 by 10,000, depending upon how those elements are connected, right. So, the summary is that whenever you use a commercial structural analysis program, you need to give these 3 information at least in order to be able to run the analysis, right. 4th information will be actually about applied loads, right. So, you need to first define what material that structure is made of, then what is the cross section shape and dimensions of the elements, all the elements in which that structure is made of, and then how long the element is, right. So, actually you need to draw the structure also, and finally you need to apply some loads on that structure, right. So, 4 major inputs are required from user side, whether you are using SAP 2000 or any other commercial structural analysis program. The process is also in the same order mainly. You start with defining all the materials, then you go to defining cross sectional shapes. The next step is you start drawing the structure, which means you are giving the lengths of different elements, and finally when the model is complete you apply the loads and give the information to construct F vector, applied loading vector, right. So, if I just summarize the whole process, kind of a workflow in any finite element based program, it will start with the structural idealization. Obviously, as a structural engineer you will be given with the initial trial sizes and trial design drawings of your structure by the architect, but they will not be finalized until you pass through the process of structural analysis and structural design. So, when you are given with the trial drawings, you should idealize that which components in that structure to be built in future need to be idealized with which component in the program, right. So, each of the structural analysis programs offer you an inventory of elements, like frame element I show you one example, but there can be 2 dimensional elements or 3 dimensional elements also. So, when you model or actually draw your structure in a finite element program, you need to first decide that okay, beams should be modeled using frame elements, slabs should be modeled using shell element or 2-dimensional area elements, or footings can be modeled using 3-dimensional elements. So, you need to first come up with this idealization. Then the main thing which actually we need to provide to the finite element software is material properties, cross sectional sizes, member lengths or the geometry of the structure. Programs, all of them will use these 4 things to construct the global K matrix. Then you need also to apply loads. F means like constant loads, or F as a function of time means loads can also be dynamic in nature, but we will be restraining ourselves only to static loads in this session. So, all the loads, for example, point loads, concentrated moments or varying loads, any loads you can apply at this stage. You also need to define support conditions for your structure. So, you need to tell the program which particular point is fixed support, which is roller, which is pin, right. And then you can proceed to run analysis case. This is something which finite element software can do for us. So, all the green boxes we have to provide to the program, and all the red boxes the program can do for us. It can solve this equation, give you all the design analysis outputs. It can give you local forces like shear forces, bending moments, axial forces for example, and all that. And several of the finite element programs also provide you the facility of automated structural design. So, you just need to select the building code which the program should simply implement, and they can perform design calculations also and give you the final geometry or final amount of required material, final sizes and everything. Some of the programs even can do detailing, right. So, there can be an automated detailing programs also, but obviously detailing is more of an art than science. So, you need to take care of many things in order to actually come up with a practical constructible detailing. Many cases this is done manually by structural engineers after the process of design is complete, right. So, it means that today we should focus only on these 4 things: how for a given beam, column or given frame we can provide these 4 things to the program. Then we will apply some loading to it, we will define some support conditions to that structure, and then hit run analysis, and it should give us readily bending moment diagram, shear force diagram, deflected shape, rotations, strains, and all list of all the analysis outputs, right. So, I will skip with all these details, but this will be the typical workflow, starting with defining material, then defining cross section, then drawing the structure, which means defining member geometry, and then complete the structure with full structural geometry. If you look at the interface, I will open it in a moment, but you will see that generally the options available on top, the menus in this program, and also in many of the structural analysis programs, they are arranged in the same order. Like first there is a define menu, in which obviously you should be getting the options for defining material properties, defining cross sectional shapes and other things. Then there is a draw option. Once you define material and cross section shapes, you can actually draw the structure on a canvas, and this will actually tell the program the lengths of all the elements and their angles and geometry and connectivity. And then you can have other menus, and then there is an analyze menu. So, once you are done with defining the load, obviously the loads will be assigned in this menu, assign menu. So, all the load application options will be there, and similarly all the boundary conditions definition will also be assigned. Like if you want to assign fixed support to a particular point, you can select, go to assign and say fixed support. And finally analyze. Here you have f is equal to ku equation built in, you can run it, and then in order to display the outputs like bending moment diagrams, shear force diagrams, you have this display menu. If you want to further carry out the automated design by this program using some given building code, you can explore this menu later on, right. But we will be actually performing analysis only. So, what I do now is that I give you a typical workflow in SAP 2000. It also applicable to ETABS, and it is actually also applicable to many other programs also. So, we will start a new model, we will select units. We can start our model from scratch, or program also sometimes offer different templates. For example, if you want a 3-dimensional frame building, they may give you a template and then you can modify that template later on. Then the very first step actually after starting a new model should be defining material properties. In our case, which is a simpler case for frames and beams, for example, the material property of concern will be elastic modulus, right. So, elastic modulus we will be defining for all the materials which our beams or frames will be made of. Then we will define cross sectional sizes, like beam size if it is rectangular or I shape or any other shape, and what is the size of that beam. This information will allow program to determine capital A, like cross sectional area, and the moment of inertia, right. And why I enclose it the material property also in that, because while you will be defining cross sectional shape, you will be associating a material also with that, right. So, you will be defining saying that okay, my beam is 0.5 meter by 0.5 meter, but at the same time you have to select which material it is made of. So, the material which you defined earlier need to be linked to that cross sectional property. Third step will be that once you have all the cross sections which your material, your member is made of, then you can start drawing your structure. You can have grid lines on a canvas which can guide you how to draw your structure. So, actually you are giving lengths and connectivity and angles, all that information to the program, right. This will complete the process to determine K matrix by the program, right. Depending upon structural complexity, it can be, as I said, 50,000 by 50,000 order matrix, right. Then next step should be define loads F vector. It is actually a 2-step or 3-step process in SAP 2000, ETABS and several other programs. First is that you start with defining a pattern of load. So, load pattern is kind of a container in which you will actually add some applied load values, right. So, first you will start by defining a pattern, then you will actually apply the point load or area loads or uniformly distributed load or any other load type, but you will associate each load with a pattern, right. So, think of pattern as a container, empty container, and then when you actually select an element, give it some load value, you have to associate that value and add it into some load pattern, right. So, I can apply point loads along the length of the beam and add them to a particular load pattern, and then later on conduct the analysis for that pattern separately, right. So, that pattern actually will be called in what we call as load case. Analysis will be conducted for load case, right. So, load case will be a bigger container containing your load patterns. You can combine two different patterns in a load case, and then program can apply that case as a whole, right. You can also create a different load case for each of the patterns separately, right. So, I will demonstrate what does it mean, but actually it is a 3-step process: defining pattern, then actually applied loading but associate them with different patterns, and then make a load case in which you call those patterns depending upon in which order you want to apply that loading. So, this information will actually complete the process of constructing the F vector. Then you need to apply the joint restraints or tell the program which of the points in the structure are fixed support, which is roller, which is pin, which is free, right. So, this is the joint restraints option, and once you done that, now you are ready to run the analysis, right. So, if for example, you are performing dynamic analysis, like your applied loading contains a value which is fluctuating with time, then there are additional steps, but we won't be actually doing it in this demonstration. We can directly go to our run analysis case, and then program will be able to report all the output, right. So, then you can go to display menu to display all the analysis outputs and plot them and then evaluate them, right. One last thing before I move to the program itself, that the program comes with a lot of learning resources. So, you will see that when you install this program, in the help menu, in the last menu, you can go to the program documentation, and then in the manuals button you will find a whole list of all the required documentation to learn this program or to understand which feature is implementing what science actually or what equations, right. Computers and Structures, the main company which have developed this program, also have a very good YouTube channel using which you can access tutorials. So, in playlist you can see that SAP 2000 have a separate playlist starting from very basic features up to some advanced analysis. So, program itself is very detailed, but I will give a quick primer today to just start with like 2-dimensional frames or 2-dimensional beams, right. I also have a YouTube channel where I list several of the tutorials or demonstrations, solved examples using either SAP 2000 or ETABS. So, now let us work through this example. I have taken it from your textbook. It is actually an indeterminate beam, and it has given length, the elastic modulus is given, the member properties like member cross sectional areas are also given. This elastic modulus is corresponding to concrete, and the member BC have these rectangular cross section size. Member AB has larger cross sectional size, right. So, from A to B, although it all looks like same beam, but from A to B it has a slightly higher size, from B to C it has slightly lower size. It has a fixed support on left end, and then you have a roller here and a roller here, and it is made of like 2 spans 6 meter each. AB is subjected to a uniformly distributed load of 3 kilonewton per meter, and BC is subjected to a uniformly distributed load of 5.4 kilonewton per meter. In your textbook, actually I took it from some later chapter where the slope deflection method or moment distribution method is used to solve this beam. They are methods to solve indeterminate structures, they are classical methods, but as I told you that none of the commercial programs utilize those classical methods. They are good for learning and developing concepts, but as far as the real building projects or complex shapes and geometries is concerned, it is mostly finite element analysis, right. So, I also took the solution analysis solution from the book. It is a solved example. So, we already have the shear force diagram SFD and the bending moment diagram of this beam, and it is determined using one of the classical methods, right. So, now let us repeat this example in the SAP 2000 and see if we can get the same analysis results under the same given information and applied loading and geometry and material properties, right. So, let me now go to the program and give you a quick overview of how you can construct this beam in the SAP 2000 and then apply this loading and then see how you can run the analysis. So, this is the desktop or the starting view of SAP 2000. It has these tabs like window 1. You can add tabs also later on by just clicking here and then add a new window here. So, you can add as many tabs on this desktop as you like. On the left hand side you have a toolbar containing different drafting tools similar to AutoCAD or any other drafting program. They will help you in actually drawing the structure on this canvas, right. So, all the finite element programs offer you list of drafting tools and then a canvas for convenient modeling. So, let me start with a new model. So, I will just click here and start a new model here. Now, the very first thing I need to select is the units, right. So, I can select the Newton meter units, Newton meter centigrade, and if someone like, they may also go with the US customary units. Default materials should be United States, or it does not actually depend. Several of these options will only be used when you perform automated design, right. Now, you can start from scratch by clicking on blank, or you can select a template. Let me start with grid only. Grid only means that when I click this option, the program will show me grid lines on the canvas, which will help me in drawing the structure, right. So, after selecting units, I can click on grid only, and then it will give me a form in which I should tell how many grid lines I need in x direction, how many in y direction, and how many in z direction. In all CSI programs, x and y directions are the floor directions and z is the height direction, right. So, whenever you have a building, the story levels will be along z direction and the plan view will be x y direction, right. So, let me start by just having default numbers like 4 lines, 4 number of grid lines in x, 4 number of grid lines in y, 5 in z, and then I can also select grid spacing in the units which I selected. Since I selected Newton meter, which means whenever I define a length or a spacing, it should be by default in meters. Whenever I apply a loading, it will be by default in newtons, right. So, let me just use the default numbers, grid spacing, number of grid lines, and the first grid line location 000 means this will be the origin of your computer model. So, I click OK, and you see that the program actually rearranged and it created 2 different views. One is 3D view. If I click on the right side, somewhere it is becoming active here. If I click anywhere on the left side, now this is my xy plane at z equal to 12, right. So, actually this is my plan view. I am looking at my structure from top, and on the right side if I click, I am looking at my structure in a 3-dimensional view, right. But currently there is no structure, it is just grid lines. They are lines for me, for guiding me to actually draw the real geometry, right. I can click on 3D view, and for example, on top you have several view options, you can explore them yourself. There are several zoom options, there are several view options also. For example, this is 3D rotate option, I can click on it and then come back to my 3D view to actually rotate my model, right. So, I can, for example, rotate it in any direction. In some cases, when the model is very complex, it may take some time to give you the required rotation view, but you can play with these different options on top, right. So, let me just again click on 3D and it will restore to the default 3D view, which is default isometric view, right. If I click here on somewhere on the left hand side, like left side of the canvas, I will be on this tab now, and it is by default my xy plane. So, I am on this view actually, but if I want to see the xz plane, I can click here and now I can see the xz plane. So, where you are on the left hand side view, you can see it by this cyan color also on the right hand side, right. So, when I go to xy plane, you can see that the 3-dimensional view have a cyan boundary, blue color boundary on top, right. So, it actually conveniently tells you that left hand side which view you are looking at or which view you are working on, right. So, I can actually click on this down arrow to go one level down, right. So, on the right hand side you can see that that blue color boundary is shifted to one level down, right. Similarly, I can go one more down and finally to the floor of my building, right, or my structure. So, now this view is now at z equal to 0, which means I am at the very bottom level of my structure. I can also even convert this one to 3-dimensional view by simply clicking somewhere and then clicking on 3D. I can toggle between different views, XZ, XYZ also, and XY also, right. So, in short, X and Y will be your floor levels, plan views, and Z direction will be the height of your structure. This point is origin and it has a coordinate of 0, 0, 0, right, and all the dimensions will be from this origin, right. So, now let's start that problem which I showed you. In that problem it is just one beam, right. So, we only need just one grid line, and that grid line should be like having only 3 points on it, because it has 2 spans of 6 meters each, right. So, I do not need number of stories, I do not need the y direction also, maybe I just need like xz plane and only one line, right. So, in order to delete these extra lines and just keep one line so that I can conveniently draw my beam, I can right click on the canvas anywhere and then go on edit grid data, and it will show me a form to modify these grid lines. So, I can delete some grid lines, add some new grid lines, and then modify the spacing between grid lines, right. Obviously, if you have a real structure with architectural drawings in your hand, then you will start with some grid lines which are most representative of the shape of your building, and then later on keep on modifying while you are actually drawing the structure, right. So, this is a common approach that we modify grid lines again and again. So, I can click on this global grid system, it is the only grid system available. So, I should go to modify show system, right, and this will give me the data of all the grid lines I currently have. So, I have the x grid data, y grid data, and z grid data. Z means actually the story levels, right. So, let me simply delete, first of all I delete all the above story levels, I just need one line at the base, right. So, let me delete this Z2, Z3, Z4, I am selecting all of them like a table and click on delete, right. So, if I click OK now and again OK, you can see that now all the above levels of grid lines are deleted and I am left only with xy plane, right. Let us only keep this line which is denoted by the grid line 1 and delete this 2, 3 and 4 also, right. So, the program actually numbers the grid lines such a way that along x axis it is calling it 1, 2, 3, 4, and in the along y axis it is calling A, B, C, D, right. So, you can see here in the plan view A, B, C and D. So, let us delete 2, 3 and 4 also from this view, and we will be left I think with one line only along which we can just draw our beam, right. So, let me again go to edit grid data and then modify the grid system and then delete 2, 3 and 4 also. So, let me just select 2, 3 and 4, 2, 3 and 4 I should select and then click on delete and then OK and then OK, right. So, now I am left with only one line along which I can simply draw my beam, right. So, obviously, this is a very simple case, it is like using a very hi-fi machine to do something very basic, right. This program is used for multi-story buildings, complex shaped bridges and other structures, but I am using it only for one beam, right. So, I just left with one grid line along which I can draw my beam now, right. So, the first step is complete, defining a suitable grid system which can help you in drawing the beam, right. I could have left that grid line as it is also and then simply draw along one line my beam, that could also be one approach, but I decided to modify my grid line to represent what I want to draw later on. So, now one thing that if I just click my cursor, or even if I do not click, I simply take my cursor to a particular point on the canvas, it actually snaps there, and at this location here at the bottom right you can see its coordinates, right. So, you can see x0, y0, z0, but there is a point here which is x6, y0, z0. So, 6 meters in this unit system, and then again if I go, there is another point, because I started with 4 lines on the other side. So, there is another grid point which is x12, y0, z0. So, my beam will be actually this much, 6 meter, 6 meter. I do not need this extra line. So, even I think I can delete this last point also. Again I can simply go to my canvas, right click, edit grid data, modify, and this 4th line actually I do not need, 4th point actually. I can even delete this one also, and then click OK and OK again. So, now I simply have one grid line with 3 points on it, they are spaced 6 meter, exactly what is the dimension of my beam, right. I can simply draw my beam on top of that grid line, and that is all about geometry, right. So, here 0 0, if you look at the bottom right, then in the middle it is 6 meters 0 0, and then finally 12 meters 0 0, right. So, if you look at the beam which I want to model, it is having 2 spans 6 meters each, right. Now, let us start the actual process, which means defining materials, defining cross sectional dimensions, drawing the structure, apply the support conditions, apply the loading, and click on run analysis, right. So, start with define menu first. The very first option is materials, then cross sectional properties will be in section properties, and then in frame sections. Beam will be categorized under a frame section, but there can be different other elements in your model also. For example, you may have slabs, shear walls, or solid elements for example, but we will be only restricting to frame elements because it is a beam, and these two things will be done, and then we will go to defining load patterns and then other things. So, let me click define materials, and this form will allow me to define a new material. I can click on add new material and then give some default things. So, keep it default, but actually in this case you know that the elastic modulus given to us corresponds to concrete, but actually it does not matter what type you select unless you are also requiring to run the automated design, right. So, but let us select here as concrete. I should select user here actually in order to define my own properties. So, the third option should be user, and then click OK. This will give you a form to be filled with many material properties, but the only property which we are concerned with in this example is the elastic modulus. So, if you look closely, the elastic modulus given is 3 into 10 raised to power 10 Newton per meter square. That is the only material property we need to define for this simple analysis case. So, we will now go to the program, and simply here in the modulus of elasticity we will simply replace it with 3 into 10 raised to power 10, right, in the same units Newton meter. So, there are other properties also, but they might not affect your analysis. They will be having some special applications, they will be invoked in special analysis cases, right. For simple elastic static analysis, you only need modulus of elasticity to be defined here. We can keep other things as default, give it some name. So, we can call it like my material, right, or beam material for example, right. So, my beam material, and then elastic modulus is given in correct units, correct numbers, and I can simply click OK, right. So, my beam material is now added to the list of materials. I can simply click OK, and now the program knows the elastic modulus for a material named my beam material, right. The next step should be defining the cross section properties. So, I go to again define section properties, frame sections, and again I should define a new section, but actually I should define 2 sections now, because my two parts of the beam have two different sizes. So, let me quickly do that, add new property, and the property should be coming from concrete, because my elastic modulus was corresponding to the value for concrete. So, actually my beam is made of concrete and it has a cross sectional shape rectangular. I can select rectangle, and here I should give a name to that cross section, right, and then give the depth and width of that cross section, right. So, both of the information were given. Member AB have this B and H, so it is a square cross section. Member BC have this different B and H, and it has a it is also a square cross section. So, let me quickly define these two cross sections. So, let me call it like member AB, which has a length width and breadth of 0.5331. Let me just confirm, it is 5531. So, 0.5531, and same is the width also. So, it is a square cross section, right. So, I call it member AB, I give the name to this cross section as member AB, and now I have to associate a particular material with that cross section. I should tell the program that what material this cross section is made of. So, I will be selecting my beam material, which I just defined earlier, right. So, this is the input required while defining a cross section shape. I can simply click OK, and member AB is now saved as one of the cross sections. I can add a new property for member BC, again click on rectangle, call it member BC, and this time give the different cross section size, which is 0.5 and width is also 0.5. Associate the same material with that cross section also. So, I just select that my beam material and click OK, and then both of the cross section shapes are also defined. I can click OK again, and now the program knows what cross section shapes my structure can take, right. So, now the third step should be drawing the beam now. For that I can go to draw, and then I can simply select draw, quick draw frame or draw frame. Both of the options will be used to draw a frame. They work in different ways of convenience. So, if I can simply select this line button, I can do it from here, or I can also just select it from the toolbar on the left hand side. So, it is draw frame / cable, right. So, let me just click on that. When I click that, it is asking me what member or what cross section you will be drawing now, right. So, I should select member AB, which is by default selected. I should click on one point, and then I should left click, same left click on the one point, and same left click on the second point. So, the program actually draw that element. That element is given the cross section of member AB, and the cross section named member AB already have the information about material, right, my beam material. I can right click somewhere to discontinue that element, and then left click again from here by selecting a different cross sectional shape member BC, and then click here, and then again click here, and then right click somewhere else to discontinue that element, right. So, what I did actually, I draw two frame elements. To one I give a property member AB, to other I give a property called member BC, right. I can click on this arrow again to come out of that draw mode, right. So, now I have two elements, I can separately click them. So, one is this one and the second is this one, right. I can click on this button, which is clear all. So, it will go out of, it will deselect the selected object or selected element. So, please do play with all the drafting tools, all the selection tools here. They are like snap to a point or snap to a line and all that, right. So, now you have your beam element containing two parts. One is having a different cross section, other is having a different cross section. Now, what I can do is I can give this point origin a fixed support, then middle point is having a roller, and then that end is also having a roller, right. So, let me just quickly confirm, yes, this is fixed support, then after 6 meter you have a point where you have a roller, and then you also have a roller here. So, let us quickly apply the restraints. For assigning restraints, you have this option in the assign menu. In the joint option, you have this very first option, restraints, right. So, you can select a particular joint, go to assign joint restraints, and then select which kind of support condition you want to assign to that point or that node, right. So, let me select this point. So, this small cross actually means that one point is selected. You can see it at bottom left also, may not be very visible, clearly visible, but it says one point selected at the bottom left. So, while it is selected, you can go to assign, joint and restraints. Restraint means the support conditions or boundary conditions. You can simply click on the fixed support, all 6 degrees of freedom will be locked, and then you can click on apply, right, and then click OK. In the 3-dimensional view, you can see that there is a green symbol here. This is a symbol of fixed support in this program, right. Similarly, let me click on this point as well as on the other end, this one and this one in the 3D view, and give them these restraint of a roller support, right. So, again I go to assign, joint, restraints, and this time let me select roller here, this is roller, right. So, let me click roller. So, only the vertical translational degree of freedom will be restrained, which means it will act as a roller support, and then after clicking roller I can click apply and then click OK. So, now you can see that additional 2 green symbols appear, they are the symbols of our roller support in SAP 2000 and ETABS and several other programs, right. So, now this is your beam, geometry is completed, your support conditions are applied. Now, loading needs to be applied, right. You can rotate this model in different directions and you can check. You can also extrude this view also, for example, click somewhere in the 3D view and go to this view options, display options, and in display options you will have a view, you will have an option called extrude. Extrude means that it will show you the actual size of the cross section on that view also. So, please explore these display options also. When I click apply, it actually shows you the size of that cross section also. So, you can see that the left part is slightly bigger than the right part. You can rotate it to visualize and all that. Obviously, these kind of views will be very helpful when you have a real 3-dimensional building, right. So, now let us come back to my same 2-dimensional view or unextruded view. Let me just move it to click to default 3-dimensional view. Now, this is my member AB, next is my member BC, both have the uniformly distributed loads, but different loads, right. So, the next step should be actually applying loads to this before I actually run the analysis. So, in order to apply loads, I will go again to define, and first thing I will do is load pattern, right. So, I will define an empty container and in that I will add the 2 uniformly distributed loads and run that analysis for that container, right. So, load patterns I will go and define a new load pattern. For that I need to fill this form, actually give this new load pattern a name. So, let me call it UDL, uniformly distributed load, UDL, and I have to select its type. Let us select the type as other, right. Since I will be actually putting my own loads into that container, so I do not need to select a particular type, I can simply select other as the type. So, it will be a default empty container of loading, and just click add new pattern and this will be added to the list. So, now UDL is added as an empty container in which I can apply the actual numbers of loading. I can click OK. So, container is ready. Now, I can click on one element. So, now you can see one frame selected at the bottom right, bottom left actually. So, one frame selected means that your one AB part is selected. That AB part is actually applied with a uniformly distributed load of 3000 Newton per meter, because your units are Newton meter. So, it is 3000 Newtons per meter. So, let me show you where you can apply a uniformly distributed load on a frame element. You will again be going to assign and then frame loads, right. Many of the features are like the names are self explanatory, and in frame loads you will be going to distributed, right, because it is a UDL or uniformly distributed load. So, you can click on distributed, you can select that container in which you want to apply that loading. So, in the load pattern, here you should be appearing a UDL named pattern. So, let me select UDL as the pattern. The load direction is important. So, let me just select gravity as the loading, right, but I could have selected the like x direction also. So, now you know what is x, what is y, what is z. X and y are the floor directions and z is the upward direction. So, gravity by default means minus z direction, and then uniform load value I have to give here. So, it is actually, let me see how much it was, 3000 Newton per meter. So, let me go back and just type 3000 here, right. So, now uniform load of 3000 Newton per meter will be simply applied when I click on this apply, right. I can also apply trapezoidal load, like load starting from some lower value up to a certain value along the length and then stayed there constant, then decrease, but I won't be using this option. So, simply uniform load of 3000 Newton per meter, replace existing loads means that if there is any other load, which there isn't any, but if there is any, this option will replace it with this number. So, I will simply click on apply, and now you can see, let me just select the XZ view on this side, because you will be seeing the load applied also on that view. So, XZ will actually look like this, right. So, now in this part you have 3000 Newton per meter load is applied. Repeat that process for the member BC. So, I select BC now, go to assign frame loads and then maybe again distributed, and this time the load has a different value. It has 5400 Newton per meter in my units. So, let me just type 5400, but obviously I have to make sure that the load pattern which I am using to add load in is named UDL, which I first defined. Direction is gravity, value is right, and I can simply click on apply and then OK. So, now you are complete with geometry, restraints, applied loading, right. So, we are ready to run the analysis now. It will solve f is equal to ku to give you all the other outputs which it can determine, and we can then compare these outputs with, for example, the shear force diagram determined using our classical method, or bending moment diagram determined using a classical method. So, let me now go to define load case. That is the last thing I need to do before running the analysis. So, first I went to load patterns, I define an empty pattern, then I put loading in that pattern. Now, I am going to load case, right. You can see that there is a default load case which is automatically created when you defined a pattern, and the name of that load case is same as the pattern, its name is UDL. You can modify it and then you can see what type of analysis it is. It is static analysis because your loading was not time dependent. It is linear analysis because your computer model is linear, it has a constant elastic modulus, it does not have a feature to go into non-linear range, right. So, elastic modulus will remain constant forever for this model, right. So, you can check that, but program can automatically create a load case once you define a pattern and then you add loading in that pattern. So, you can simply review this option before running the analysis. I can simply go to analyze now and click on run analysis. The same button is here also in the toolbar also on the main front page. So, I can simply click on run analysis, and now there are two default load cases which were already there. You can just select them and click on do not run the case, because you only want to run the analysis for this UDL case, right. So, you can set their action as run and click on run now, right. So, this will be your magic button, run now. which should simply calculate everything for this loading for this beam. Before that, obviously I need to select it, save it. So let me call it like test beam, right, and save it, right. So it just run in 2 or 3 seconds because it was very simple beam, simple case. So now let us quickly see its SFD, BMD, deflected shape, and see whether it is matching with what we get from classical method or not. So go to display. After running the analysis, the default view which you will be seeing is the deflected shape, right. So this is an exaggerated deflected shape which program is telling you, and you can see the name also, its deflected shape for the case UDL, right. And you know that in this particular case you have one pattern, that name is also UDL, and in that pattern you have 2 forces, both were uniformly distributed load applied to each member separately, right. So let me go to display now, because now the analysis is complete. I can show you some of the results. I can go to, for example, show forces, and I can go to frames, like forces of frames, right. And in that again you can first select for which load case you want to show the results. The only load case available is named UDL, and this is very important. You have to select which type of force you want to plot. So let me select, for example, moment M3. It is the primary bending moment produced by the vertical gravity load which I applied, gravity direction load actually. So if I select M3, it should give me the bending moment diagram. If I click OK, it should give me the bending moment diagram of this beam under the load case named UDL. I can right click on any element to see an enlarged view of the bending moment diagram, and also to confirm the values also. So let me right click anywhere on this member AB, and this form will appear, and this will show me with my mouse scrolling. It can show me, for example, the shear force diagram, bending moment diagram, this is the applied loading and reactions, and the last is actually the deflected shape, right. So for example, on the extreme left corner, if I click here, the shear force is around 6.4 kilonewtons, right, and bending moment is around 4.0 kilonewton meter, right. And if I go to my classical analysis results, you can see that at extreme left end I have 6.4 kilonewton shear force, and bending moment is also, it is minus 4.0 there, and here it is minus 3.95. So very close, maybe the error is just less than 5% or so, right. One thing is that your textbook might be using a different sign convention. So therefore the bending moment diagram and shear force diagram might look opposite of what you see in the program, right, but the numbers are exactly same. Because of opposite convention it may look opposite, right. Similarly on the left hand side you can confirm the numbers for shear force, bending moment, and they will match with what you have on the left hand, on the right hand side of the member AB. And same you can click on member BC to confirm that its shear force and bending moment diagram is exactly same. So this BMD is same as what you get this BMD from classical analysis, it just flipped in the opposite direction, but the values are same. Let us quickly see the shear force diagram. From the same option, go to display, show forces, and then frames, and now let me select shear V2, shear 2, and click on apply and click OK. So this is the shear force diagram which is exactly matching with what you get from the classical method, except that the program is using opposite sign convention from the textbook. So again you can confirm, for example, this peak is 19.4. Let us see in the program this peak. I right click on this beam, and exactly the left side peak is 19.37 kilonewton, right. So exactly same number, very less error. Same is for bending moment, but additionally you can also see deflected shape, you can see other analysis results. So once you run any analysis, please do explore this display menu after the analysis. Previously, before running analysis, all the features won't be alive, but after you click on that magic button, all the options will come to live, and then you can select and play with different graphics of results, right. So, please do use this program for your project or any of your assignment to get a hands on experience also. I will upload this PowerPoint file, it contains my email address. So, if you have questions later, please do not hesitate to email me, and I may respond with the required information, right.